Hello again, simple Haskellers, who are not so simple. So this lesson is on monoids and semigroups, which are two very, very similar concepts. And so as you can see, if you have done the list and recursion, video, then this is the same code from that video, and there's a good reason for that. And the reason really is that monoids are kind of when we're getting into our first type class about common structure in Haskell. And so with that, it's kind of a good time to point out that in terms of complexity, for real world Haskell, what we're actually going to do, this is really a fair demonstration of how complicated our types get in terms of being a product type. If you guys recall either, where we have either, which is either takes two type arguments to become to become a real type, and that will bring into play two data constructors of left and right with the corresponding types. So of course, just as review, if this was a string, then this would be a string, and then next, if this was, let's say, my custom type, this would be my custom type. And so really this is, and I'm lying when I say this is as complicated as it gets. It does get slightly more complicated, but even then, it's not too much more complicated, and it's not even the extras that I haven't really covered yet. You can kind of, once you understand how they work, which we will get to a point where it is extremely understandable, then you have kind of seen the full complexity of real world Haskell, I suppose. At least to create your own programs, kind of thing. Any library can get arbitrarily complex, and there are libraries that do that, but yeah. So, point is, for the most part, we have covered the complexity of what we need to. But now we're getting into monoids, where we're saying, okay, about this complexity, how can we take a shortcut? And this is 100% where we're I've been talking a lot about shortcuts in Haskell and how that's all of advanced Haskell. I would say this is advanced Haskell in the sense that you do not necessarily actually need this. And it's a common pattern, and that's one thing that Haskell is really good at, is noticing common patterns in this very simple language and taking advantage of them. So that's why we have more advanced concepts in Haskell, such as the monoid. And so, to start with, now we're talking about patterns about structure. What does that actually mean? Well, that means a lot of things, and it's a very vague way of saying something. But for this lesson and the next lesson, that's exactly what we're talking. Is exactly what we're talking about. We are talking about patterns about common structure. And so monoid is our kind of first example of that. And if we enter into a REPL, oh yes, let me go and fix that first. There we are. Oh, except I'm going to need to. And then we are good. So, I was in lists. What is a monoid? So I'm just going to start by looking at the monoid type class. And so, well, I see that I made a mistake in talking about monoids first. I grouped the two in together, monoid and semigroup. Let's start with a semigroup. And I think even the name itself kind of is a bit more explanatory. So a semigroup has one real function here. And even we can see that for our minimal pragma being those brackets with the, this la here, we can see that all we need to define is this, the opposing angle brackets. So I'm going to call this the semigroup function for the purposes of the lesson. Oops. I accidentally tried to run that, which makes no sense. But what does this do? So the easiest example is, let's say we have two strings, red and dead. Red, dead, and you know what, we'll put a third one in here, red, dead, redemption. Hopefully I don't get any advertising, whatever, copyright, if they don't want me talking about it somehow. And I can put these together by using this function. And I've done this wrong because really I didn't need that. So I just wrote Red Dead Redemption. And so the reason I can do that is that a string, if you recall the info for a string, it's just a list of car. And if we look at what some of the instances are for a semigroup, we can see that a list of A qualifies as a semigroup. And so, I will say, I don't know if this really helps us at all, but we are still kind of dealing with, I will call them a simpler class definition here, in that we have some type A, which is a semigroup, and we can take this A and do some operation with it. And our method uses that same A type variable to define its type signature of the type of the functions that it has, such as the semigroup function. And I was gonna try something else here. I want to see if text 1. This is an experiment. I want to see if this also applies to text, because I believe it does. This is also gonna fail. Right. Import data.text. I have to set the extension of overloaded strings. And I'm just basically trying to see if text is a semigroup. And yes, it is a semigroup. The reason I had to check that is because so the place in which semigroup is defined does not define text as a semigroup. I'm assuming just because this module would have been written before text was. But if I go to data.text and I look up the text, I hate Chrome for that. I can see that it is an instance of semigroup and a monoid. And so the point I'm trying to get across here is there are very few actual things that are semigroups, like in the most simplest kind of sense. There is, even if I look at, there are, I will say, make a division between what I think of as kind of being a semigroup and a monoid versus what you can actually do with semigroup and monoid. And that's hence why I brought up this list lesson again. And so when we went through, what we saw is that there was sort of a pattern that emerged. And, us being lazy Haskell developers, not just the language, we want to take advantage of this pattern so that we can write less code. And so, where's a good example of this? So, product is a great example. Product and are both two great examples. So, why is that? So, we have sort of one particular operation, I would say, that defines the behavior of our overall function. So we're going to do x times the result of some recursion. And so this is going to end up being x times x2 times x3 times x4 all the way up to x n, which is where n is the last element of the list. And that's, of course, just because of recursion, but, recursion is really just a means to an end where we are, multiplying all of the elements of the list into a product. So, yeah. So, and then that kind of defines, I guess, in a certain sense, what a semigroup is, and that these can be combined. I wouldn't say it really separates. I will say for the weird, we'll call them monoids and semigroups. I haven't really looked into how exactly the semigroup is defined. Although actually, I guess it would be quite simple if I thought about it. But I'm kind of jumping all over the place, so I will come back to that thought. But back to the important stuff. And this is really now specifically talking about monoid, and I am jumping around, but this is more, and I'll explain how this relates more to monoid, but what we see with both of these is that we kind of have this end case. So we have the end of the list, and we have to decide what to do about the end of the list in order for our function to terminate properly. Because we're going to get to a point where with this recursion, with going down the list, we end up with pattern matching. We end up with a case where we pattern match on an empty list. And so in the case of product, we say 1. In the case of and, we say true. So, why do we do that? What is the common element here, right? Because we have, in both cases, we have, some operation on, some comparative operation, we'll call it, or some sort of operation with an A and a B that gives us a C in the most general sense. X and something else is going to result in something else. And when I say A to B to C, that's really the same thing as plus. That's no more complex than plus, where we had, for example, if it was applied to a particular type, it would be int to int to int, which is just saying it takes two things and returns a different thing. Here in this case, it's actually not a different thing. It could be in the sense of when I'm saying A to B to C, it could be a different thing, but here it is not. It's A to A to A. So, yeah. But so that allows us to merge a list of things. We have this end case, which just is what this is called is our identity case. We do this because when we merge with this identity case, nothing is different. So like if, for example, if this is true and true, and we can say that we have an identity case, for example. So let's think about the identity case here. So if we have true and so we have two cases. We can have the accumulation of all the prior events end up as this false, or they end up as true. And now we have to combine it with the last event. If we do true in this case, true and true is going to give true. True, false, and true, this gives us false. So what can we deduce from this in terms of our patterns? Well, this last element is effectively pointless. This is the only reason that it even needs to be there is because we need to do something just based on how we're recursing and pattern matching. And that's really it. There's no other reason besides why we have this last and true. And so that recursion being a very important practice, identity cases are also a very important practice. And so that identity case is the only difference between a semigroup and a monoid. So if I might as well just bring this up here. Is this a different... Yeah, so here's what we talked about with semigroup, which is just an associative binary operation is how it's defined. If you're an example person like me, this is what it means. So it's just, merging this first group with this second group. I guess that's why you call it semi, because two... I don't know. But monoid is basically the same thing. And if we look at mapend, it's the exact same thing. And we can see it's literally mappend is defined as this semigroup function. So the only difference here is this mempty. And so mempty, going back to our sort of identity cases, where was it? Well, empty. So I guess the base case in my mind for empty when it comes to lists is I think if we can actually probably look at the list. Yeah, here we are. Empty for list of A is just the empty list. So and that's because it's it's kind of an identity in a function in a sense, in that it doesn't really do anything. Like for example, and why it fits in this case, why it fits with this type class and the laws of this type class, getting into the kind of math, I suppose, or the mathematical rigor, is that this mempty has to do nothing when combined with its same type. So this is different from cons, because if you recall cons, if we look at the type of the cons operator, we see that it takes an A and a list of A and a list of, and then returns a list of A. If we look at the type of this, it takes some type A, another type, and another of type A, and returns that same type. So, for example, we could fill this in to be a list of A, because we can see that list of A is a monoid. So we can fill this in to say that list of A works here. And then since we've applied that, the internal A, doesn't need to be a semigroup, just the list itself, because we've asked what is a possible semigroup that could fit for A. And again, that might confuse you because we're like going from, a type signature with a list of A, which is somehow filled in by having a list of A. And yes, that makes sense because, lists are a complex type, and so we can do certain functions on lists that we don't need to think about or care what is inside that list. For example, we have done this operation where we have done this operation where we are putting together two lists, and you can start to notice a similarity. Like, let's say this is even a list of lists. We're going to have a similar result to there's a similar pattern that emerges regardless of what is inside the list. And just from another lens, to really fully explain it, why would we need to care what is inside the list to put the elements together? At the type level, we need to know that the contents are the same, and that's just because the compiler will complain in order to keep us working with homogeneous lists, but there is no actual reason that we need to think about what is in the list in order to do that operation. And so for that reason, we can start to think of a list as a semigroup and a monoid. And so, that's the only real case in which I would say it's like a true semigroup or a true monoid. Text is definitely, text and byte strings, byte strings are definitely, it makes sense how those could be a semigroup. I'm not even 100% sure if they are a semigroup. I believe they are, and I think I can figure this out pretty quick. Import data.byte string. Oh, it is a monoid. Yeah, so that makes sense. And, yeah, of course that makes... Well, because I guess, yeah, that makes sense. So, it's another... And I believe even, I guess I'm not sure how byte string is defined, but it kind of makes logical sense to think about how... byte string, text, string, and lists are all kind of these real semigroups, and that they can just be kind of concatenated all together. But then we also have cases like product and and. And so product and don't really fit the kind of scheme of... That's what I'm looking for. We're dealing with... We're not returning a list or working with lists and putting the two together, but we are putting together numbers. And so could we have int as a semigroup? Now, that would not work very well because, how do we intend to use int? Are we going to add it together? Are we going to multiply it? Are we, I guess that's really it. But, add together, yeah. But So now in that more general sense, and I kind of had to do some review just to kind of understand this myself, but what a monoid is meant to be in, I guess, more rigorous mathematical terms, or at least for how it's used based on those rigorous mathematical terms, is that it... Okay, here's an example. So I have a scraper which goes out and just goes wild. It goes on to a ton of different pages, and I was going to build a map of all of those so I could keep it as a manageable data structure. However, I realized by trying to run it that it is extremely slow if I do use maps every single time, and I keep merging and doing unions of maps. So what I've decided to do instead is just return it as a list. And so I'm going to build a list where, the first scraper is going to go and it's going to put element 1. They're actual data structures, like they're triples of stuff, but we're just going to say they're numbers. So, if we were to scrape some number off of a page, we just found the first number on a bunch of pages when we're scraping, and these scrapers can effectively give birth to other scrapers that go and do their own scraping on links that they found, and it just goes wild. Now, what we're going to eventually end up with, so each page is going to find its number, and how do I kind of rectify the results of each page with each other? I'm going to end up building a list where it's like just this kind of stream of data, and so what it is in this sense, in the most general sense here, is kind of a collection of results over time. And so we could fold our results over time, where we're kind of saying if we wanted to ask how things change over time, we could do that by simply going by index, because we placed those indexes in a particular order due to a particular reason, which is that this is when the source has created this index. Maybe that was a little bit complicated in how I said that, but yeah. Now this, but anyways, the key point is that for some reason we built a list which is in chronological order, and so we can ask questions about that. And so I'll just kind of go through some of the examples here. Let's start with the easiest one, and that is sum. So let's say we did want to use int as a semigroup. The only thing that we would need to do is to say how we intend to use int, and so we could wrap it as a sum. So I could, for instance, import data.monoid, and if I said data.monoid, so if I said sum1, so I construct a sum 1 sum 1, and so I can see that I have this wrapped in get sum, and this would be, this is obviously not the point of get sum, but this is how I get that number back out. Let's say I wanted to, but here's how I would use sum, is by using my
contains a built-in screen reader called VoiceOver. If you know how to use
that's so
VoiceOver,
annoying.
press Command F5 now.
I'm currently fixing my Mac at the same time, and that's what just happened. But if I want to say so how this reads in Monoid language, I suppose, is put together sum1 and sum2, and we get sum is get sum3. So I could do, again, get sum, and I would get 3. So here's where I would really use that, is I would say I intend to add all of these numbers together. And this is even not a very useful, useful function here, I would say, because I don't get why you would use these in all honesty, but, there is definitely some cases I have seen where it does make sense to have a monoid just for the sake of control flow. And so, pretend that this is like a better example of where you'd want to use it, and that there's not a just simply easier example, because we will get to some, but no pun intended. But this is, I think, just the easiest to illustrate example. So I could put my answers or my results at each step to this list as a sum. And that would mean that I can use a function from the Monoid class called mconcat. So let's say I have that list of sum1, sum3, sum5. This will concat all of my individual elements together. So mconcat taking a list of the monoid in particular, the list of a list of the monoid in question. And so this could also be a list of lists. This could be a list of 1, 2, 3, 4, 5, 6, 7, 8, 9, and voila. And now the only other ones that don't really fit this mold, like you can see any just really is the same thing as, it's a very similar function to and, in that it's dealing with booleans. And if we look at the semigroup instance of it, we can see that it's effectively wrapping true. So this will do nothing. So, like, for example, if I was to concat all true with, all, this would be more like this. Then it would do nothing, because it would just do nothing, because that's the nature of how all works. It's asking, are all true? So every single one of these would have to return true, and if there's a singular or false in there, then this will fail when we put them together. Voila. And there's a couple of different Boolean type wrappers here. Bool wrappers. Num wrappers. Product. So this is quite literally just a monoidal implementation of product. And then, I guess the last case is this kind of category of maybe wrappers. So, I actually haven't used these, but I am curious about how they can be used. And so I guess what this is saying is take the first successful case, I believe. So let me try this. Let me run this. I know that this is obviously going to give me just hello, but what happens if I was to say if the first case is nothing, yes. Okay, interesting. So the first case that returns that is a just would succeed. And I'm not gonna lie. At first, I thought it was just literally whatever the first one is, and I'm like, I don't get why you would use that, but I guess I haven't looked into it. And so I guess this is looking for the last successful case. And so this is okay. And where did I see this? So I think where I saw this was with I want to say something to do with authentication, and I think the use case of it was that you want to take the last successful authentication. But I mean, I won't get into that because I don't really know. This is the first time I'm actually understanding first. Because, again, I don't use it. I haven't come across a case where to use it, so yeah. But that's really it. That is Monoid in a nutshell. And so, just before we get to any of the more complicated, well, they're really not complicated, but, what we've talked about here is we have talked about something that a type class, or two type classes, semigroup and monoid, which are just simply talking about the structure of its arguments. So, yeah, and that statement might make a little bit more sense with the next lesson that I will get into. But if it doesn't make sense or doesn't help you with this, you would really just do well to understand that it is just a type level implementation of these kind of two functions and so on and so forth. But that is really all I can add to that. Thank you so much for watching yet again. I see that there have been some people liking my videos, which is pretty awesome. I don't really, obviously it's not a big channel at all, but I really do hope that these videos are helpful. If I can help even just one person kind of get started with Haskell, I think that is huge. Haskell is such a beautiful language and definitely makes my brain have to do way less work. So definitely grateful for it, and definitely would love to get a bigger community around Haskell. So yeah, but again, thanks for watching and happy coding.